So the first nuclear process we want to talk about is fission. Fission was discovered by these three people, Lisa Meitner, Otto Hahn, and Fritz Strassmann. And what they did was they started with uranium and they hit it with neutrons. Now neutrons are very small, uranium is a very large element, and yet in the things that came out, they found barium, which is a middleweight atom. So they wondered, how could we start with a large atom, add a very small neutron, and get a middleweight atom? Just a few weeks later, Meitner and her nephew, Otto Frisch, figured it out by saying, what if this uranium, when it's hit by the neutron, splits into two? That's what fission means. Fission means split apart. Then if it splits into two pieces, the individual pieces would be medium weight atoms like the barium. So what happens in fission is that we start with a uranium, and it turns out it only works with uranium-235, and we add to it a thermal neutron, 1. That gives us uranium-236. But the uranium-236 is unstable, so it will split apart into two pieces, each with roughly half the total mass of that uranium-236. So for example, it could conceivably split into two palladiums. That's atomic number 46. Each with a mass number of 117, and then have two neutrons. It turns out that's not a very likely split. Typically, when the uranium splits, it doesn't split exactly evenly. So as you see here, most of the time, the split is about 140 on one side and about 90 on the other side. And there are typically some free neutrons that are released. In any case, this final situation, where they're split apart, has much less total mass than the initial 235, uranium-235, and neutron. And that extra mass is released as energy. A typical case is like one shown here, where the uranium-235 plus the neutron becomes uranium-236, which splits into a xenon-140, strontium-94, and two neutrons. Typically, the two daughter products are quite unstable and go through several very rapid decays before they become stable or semi-stable elements. So we can see that for this example right here. The xenon decays quickly to cesium-140, which decays to barium-140, then to lanthanum-140, and finally to cerium-140. Notice we are increasing our atomic number each time, and the half-lives, while they're increasing in time from 14 seconds to 64 seconds to then 13 days and 40 hours, so this one's not an increase, they're still very short half-lives. These decays release additional energy and add to the total energy we get out of fission. For the strontium, it decays to two other elements, which I don't remember their names off the top of my head, but again with fairly short lifetimes. It's not hard to see why the decay products of uranium should be unstable. If we look back at our diagram of stability, the uranium was way over here on this region of the graph. And then we cut it in half. So we cut it into half as many protons and half as many neutrons. But if we're cutting both in half, we're following essentially a straight line from here back to the origin, which brings us well down onto this side of the line of stability. Remember, the line of stability is bending over here. By cutting in half, we're going straight back along a straight line and end up on the right side of the line of stability, where we have too many neutrons. So the natural tendency is for those neutrons to decay into protons by beta decay to get us back onto the line of stability.